So this week I'm happy to introduce Mike Zemcov. So for those who've been at UBC for a long time, they might remember Mike was an undergrad in our department. So he went off to the UK and then the US, and now he's a faculty member, recently got tenure at the Rochester Institute of Technology in Rochester. Mike works in cosmology, but he builds instruments to study large scales in the universe. And in particular, he's been involved with rocket experiments and satellites of various sorts, and he's sort of packaged that together. And today he's going to talk to us about measuring large structures with small telescopes. So it's all yours, Mike.
Thanks, Douglas. Thanks, everyone, for having me. It's nice to come back and be able to talk to you all. It's interesting, you know, going to UBC and coming down here to the States and other places, and I'm constantly bumping into alums who are faculty here, there, and everywhere. You went to UBC? Oh, I went to UBC. So, you know, the department has a sort of outsized footprint, it seems like. It's kind of amazing. Anyway, we can talk more about that later if you want. So I'm going to talk today about one of the sort of branches of my research that kind of hangs together in a nice way, which is about building small telescopes, and specifically small telescopes in space. I'm going to try to motivate why you would do such a thing, and the kind of things we can learn. I know this is a physics colloquium, so I'm going to be a little bit brisk, I think, and try not to belabor the astrophysics part too much, and hopefully be a little bit gee whiz, because I do a lot of, you know, orbital and suborbital work, and I think it's kind of fun in a lot of ways. So let me start off by just kind of calibrating you, giving you a little bit of context. What I'm interested in scientifically, fundamentally, and I always tell my students it's a good day when I actually get to do this, but what I like to think I do is answer questions about the biggest picture of the universe. And you've all seen pictures like this, you know, the potted history of the universe in one slide. Starting on the left, you know, t equals 0, the Big Bang. Very, very shortly thereafter, there was this period of inflation where the universe basically expanded from micro scales to macro scales almost instantly. After that, we have a pretty good understanding of what the history of the universe is, including things like nucleosynthesis, which was happening, you know, minutes after the Big Bang. And then later, as the universe expanded and cooled, the release of the cosmic microwave background that we study to sort of understand the early universe. And then later on, the first stars and galaxies get formed. We have this period we call the epoch of reionization. And then later we get things like cosmic noon, which is the peak period of star formation in the universe. And then things calm down a bit again. And we end up with a universe that looks like the one we see around us today. The question, you know, basically boils down to what are the building blocks of the universe in the sense of, you know, what's the energy budget in a sort of relativistic sense? What kinds of matter are there? What kinds of particles are there? How do they interact? And can we learn things about fundamental physics from studying that? And also, in a very connected way, how did structures form? What was the process by which they form? And by studying structure, can we go back and understand what the fundamental physics are? So those are the kind of the questions that motivate me. As you, I'm sure, know, we know quite a bit about that now. In fact, this is a simulation from the illustrious collaboration that's done in a computer showing something that will, you know, later become basically a cluster of galaxies or a group of galaxies, starting with dark matter in the early universe. And basically the story of cosmology is the story of gravitational collapse of these different components, including esoteric stuff like dark matter that we don't know all that much about, but also the light matter that we study and attempt to understand things like how did stars form? How do stars agglomerate into galaxies? How do galaxies merge and evolve over cosmic history? And you can see in this movie here, we're watching, in this case, the gas temperature as the clock ticks forward now into heavy elements. And what we see is a sort of interaction between this gravitational collapse and then pressured matter, the baryons and so on, that are undergoing different forms of structure formation and then blowing back out into the intergalactic medium. And here again, we have dark matter showing, you know, dark matter's clustering and forming larger and larger structures over time. And eventually you can make a computer basically make galaxies that look like the galaxies we see around us today. So obviously, you know, there's a lot of physics back there and there's a lot of ingredients, and we do a pretty good job. We can make things that look very realistic and seem to match our understanding pretty well. But of course, we're not done. We keep building things. And one of the things that we do is build large telescopes, right? And the reason we do that basically runs like this. Your signal to noise ratio on point sources, if you're interested in looking at, you know, little pinpricks of light like distant galaxies, goes as the diameter, you know, of the telescope. It's the light gathering power. While the angular resolution goes as the inverse of that. So for both reasons, you want larger apertures, right? You want bigger and bigger things because you get more photons, and you also get better images of these little tiny pinpricks of light. And so by doing that, we can build things like JWST or TMT or whatever, and get better and better understanding of sort of, I don't want to say the microphysics because that means a different thing, but sort of the object level kind of physics of what's going on in these extragalactic things. As a counterpoint to that, though, these telescopes are extremely expensive, as we know. TMT here, latest estimate that I found was 2020 is going to be 2.4 billion. JWST is much more than that even. This is not a cheap game to build bigger and bigger telescopes. So the question is, especially if you're like me and you like putting things into space, what do you do? Because you don't get very many options to build things like JWST. Well, what we can observe is basically that sensitivity to surface brightness, which I'll describe a little bit more in a second, but basically the intensity over a large area goes as the product of the area, the light gathering area you have, and the solid angle, how big a acceptance of your field of view you have. We call that the entendu for people taking points and keeping score in the audience. So what that means is if you are trying to build compact things that you might affordably get into space, what you really want to do is make as big an omega as you can at a given A. That is, you're probably stuck with a small a because you're trying to get into space, and mass and expense goes as the area of the telescope. So as long as we're smart and suitably design things, we can actually do a lot with surface brightness that doesn't require big telescopes. So to unpack that a little bit, what I mean is, on the left, if we were trying to build some kind of instrument to measure a dot on the wall, you know, a fly or something, and really study it in excruciating detail, we need a big aperture, right? You have to kind of have a high magnification so you can really zoom in and see what you're looking at. On the other hand, if all you're interested in is how bright is the wall, you don't need very much angular resolution. What you really want is light gathering power. You want to capture as many photons as you possibly can. And that is the thing that maximizes your signal to noise ratio. So the picture on the right is just sort of a mnemonic of what we're really talking about here is trying to understand the universe by looking at big areas rather than individual little pinpricks. That's the name of the game. So a classic example, or now classic example of this, is the cosmic background radiation. So if you take a telescope, in this case, working at submillimeter wavelengths, so you know, hundreds of microns wavelength, and you have it a little bit with a big beam, so it's not so good at resolving individual teeny tiny pinpricks, but you play it around the sky over a big area and make a map, you get an image that looks like this. This is the cosmic infrared background. And it is encoding basically the history of star formation in the universe. And if you're clever, you can kind of tease out based on things like the color and the spatial distribution of all the light in this image, how that must have gone. When was that happening? How vigorous was it? All those things that are of interest in astrophysics. So this is just an example. It ends up that all wavelengths of light have a cosmic background radiation. The most famous is probably the cosmic microwave background radiation, which I talked about earlier, which is left over basically from the production of hydrogen from protons and electrons in the early universe. That is a very important background. People, in the department could tell you a lot more about that. I'm not going to talk much about that today, but I did want to make the point that that's just one of many different backgrounds. And each one of these backgrounds here that are labeled radio, microwave, infrared, optical, and so on, are encoding different information. They're sort of emplaced by different populations of stuff in the universe at different epochs. And they're telling us about different physics. They're telling us about, for example, in infrared, the physics of cosmic noon, about the most vigorous epoch of star formation in cosmic history, and so on. So that's the sort of theory part about what we're trying to do here, is basically build telescopes so we can study these different backgrounds at different wavelengths and kind of tease apart what must have caused them. If I make a plot, though, of the state of measurements, and this comes from Douglas, actually. I don't know if there's a newer version. This is pretty old, but I'm sure we could talk about it later. This is kind of the state of play. The CMB is very well understood. The sort of high energy backgrounds, the gamma rays and X-rays, are also very well understood. Out into the radio, that's pretty well understood too. We have a bit of a situation here. The infrared here and the sort of optical ultraviolet here, not very well understood at all. And in fact, if you look at this dispersion in sort of measurements, and the measurements are many different ways to do it and many different systematics and reasons why they would be different, we have 2 or 3 orders of magnitude of scatter here. So this is a place where we can make progress. And that's a lot of what I do with my time. Okay, so one question is why is that region so poorly understood? And a big part of that, and a sort of theme that's going to run through my comments today, is the zodiacal light. So what's the zodiacal light? Well, it ends up that the Earth and the planets are embedded in a dust cloud that lives basically in the plane of the ecliptic of the solar system. And you can see from this image here, which was taken, I believe, by an amateur person, but with a very nice camera, you can see on the right there the sort of galactic plane, typical of astronomy. Not the best picture of the galactic plane you've ever seen, I'm sure. But the thing I like about this is this band here, which people tend to discount as, oh, maybe it's sunlight from below the horizon or something like that. That's not it at all. This is actually zodiacal light. This is the light from dust that's reflecting back the sunlight when you're looking from a dark place on Earth. So the situation is that this light here is extremely bright. And most importantly, it's extremely bright compared to the light from galaxies. Now, most often, because it's a very diffuse, bright background, instruments with small fields of view that have very large apertures can kind of drill down in teeny tiny areas, and they're not sensitive to the absolute brightness of this thing. But if you're playing the game that I'm talking about today, where you're interested in making sort of big maps of the sky, this zodiacal light is a real killer. And it doesn't go away if you go into space. This is a cool picture taken from, there was a mission from the military, the US military, called Clementine, that was doing some moon science. It had on it a star tracking camera. And a group of clever people took all the pictures that Clementine's star tracker took when it was behind the moon towards the sun, and were able to build up a map of what the zodiacal light towards the sun looks like. For reference, this dot here is Venus. That's the kind of brightness we're talking about. So the problem we have is that Earth is embedded in this sort of dust cloud that has a fairly complicated shape. Looking at sort of zodiacal systems, we know there's things like dust lanes and rings and tracks from comets and all sorts of things that get sort of emplaced into this zodiacal light cloud, this interplanetary dust cloud. And all that makes removing it and doing a careful job of this background science at optical and infrared wavelengths very, very difficult. So that's what causes this dispersion here. And if we zoom in on this region, we get something, this is a more state-of-the-art version of this plot. We get something like this. The y-axis is a little esoteric, and we use it in this field for a variety of reasons. But basically, it's brightness. It's just the surface brightness of the sky as a function of wavelength here. So what you can see is if you do things like count galaxies, which are these lower limits here, you can get a limit to what's this background light, right? The background light is emplaced by galaxies. And so if I count them up and add up all the light, I'll get some limit. But if I then go out and I try to take a photometer and do basically a staring measurement where I don't care about individual sources, I just want to add up all their emission, I get stuff that's up here, you know, at least a factor of 2, maybe even an order of magnitude higher. And this has been very stubborn over the years. This situation has been very difficult to get past. But it's important, right? It's important because this difference, if it's really a factor of 2, is telling us a lot about how many stars there are in the universe. If I take these lower limits here and say, well, that's the light from galaxies, and then I say, okay, I'm going to ignore galaxies as individual objects, and I'm just going to count photons, I get twice as many. Well, that's saying that there's twice as many stars outside of galaxies, or at least some source of photons outside of galaxies than we were expecting, which is really important for cosmic energetics, right? It tells us a lot about where the matter is and what matter sort of matters. Okay, so that's the motivation for measuring at these sort of optical infrared wavelengths. I wanted to just introduce one other concept real quickly, which maybe some of you are familiar with because I know people in the department work with this, which is intensity mapping. So the question that we're interested in here is what's the large scale structure of the universe? And this cartoon here, I just want to sort of implant a mnemonic, which is that the universe we can kind of think of as being this diffuse filamentary structure that's mostly dark matter, but also faint galaxies and other things, kind of tracing out this cosmic web, it's called. And then we can think of galaxies as being the bright sort of nodes in this network, okay, the places where things are the densest. So one way, and a very successful way over the last 100 years to kind of trace out that structure, is to look for individual sources of emission and say, okay, well, these things are tracing this underlying structure with some bias that perhaps we have to understand. But the point is, this is a representative sample of what's going on underneath. So if I understand the statistics of that, I can understand the statistics of the orange stuff. What's come to sort of light over the past decade or so is that instead of doing that, or perhaps because I'm working at a wavelength where galaxies aren't really so visible or aren't pinpricks, or however you want to think about it, what we can do instead is say, okay, to heck with the galaxies. I don't care about the nodes in the network. What I really want to do is I want to make a high fidelity, large scale map of this emission. And then I want to compute the statistics of that map. And I want to understand what's going on, you know, statistically place to place. Even though I'm not really doing a great job of measuring the emission compared to how it actually is, what I am doing is developing an understanding of how much bright stuff there is, how much faint stuff there is, and so on and so forth. And that idea is called intensity mapping. Okay, so what we did, and I think this is one of the earliest examples of intensity mapping that exists, actually, if you look in the history. Obviously, intensity mapping of the cosmic microwave background, because there aren't point sources in the cosmic microwave background, it's honestly this diffuse sort of unresolved emission. Or that's kind of been the laboratory for developing a lot of these techniques. But I think over the years, people realized that, aha, we could do this at other wavelengths and really make some progress understanding what's going on in the universe. So, gosh, about 15 years ago now, we came up with this idea to build this sounding rocket instrument where it would have 2 cameras on it, and those 2 cameras would have very large fields of view, like I was talking about, very large omega, so they accept a lot of light at a given fixed aperture size, which in this case is about 10 centimeters. And then what we're going to do is have a 2-degree field of view, which is enormous, and make these, you know, unresolved images of the sky. And then we're going to have 2 of them working at 2 colors, so we can do sort of differential measurements where we kind of look at what the color of whatever it is we see and try to understand that. And what we're looking for here is, again, that sort of diffuse flocculent emission. We don't care so much about the individual stars and galaxies. We want to get rid of all that. We want to look at the places in between the galaxies. That's what we're interested in mostly. and specifically the statistics of that. I'm going to really quickly touch on another instrument, which was a low resolution spectrometer, LRS. That was working in near infrared, and that was doing more of the photon bucket, just counting photons as a function of wavelength type measurement. It ends up that these things are very complementary, as I'll go into in a second. Okay, so this is what the instrument looks like without a skin. It's actually 4 telescopes in this case, all cooled to liquid nitrogen temperature. And then we put it on a rocket, and this door here is closed on the ground where, you know, we have to keep this evacuated, so it's cryogenic and all that. But once we get into space, of course, it's a vacuum, so we can open up the door, and that lets us look at the sky with sort of an unimpeded view. So to give you a sense of scale, I'm just going to show you some, you know, hero shots here. This is how big it is. There's a grad student working on it. When you put it in a skin and then attach it to the rest of the rocket systems, things like telemetry and attitude control and the recovery system and things like that, this is what it looks like all spread out on the bench. This is during testing. And then what you do is you button it all up and you make it into a long cylinder with a nose cone on it, and then you strap it, in this case, to 1, 2, 3, 4 rockets. These sounding rockets are actually usually repurposed military ordnance, surface-to-air missiles, with the exception of this stage, which is called the Black Brant, which actually is built in Canada, and NASA purchases. So that's pretty cool. And the nice thing about working on these things is this is little NASA. You actually get to work on it hands-on. So this is a graduate student and myself getting this particular payload ready to fly. Okay, so that's kind of what we do with these things. This is what we saw in a very succinct way. This was the image of the sky we took in one field. And in fact, this is a little bit cropped. The real image is a little bit bigger and square. And that's the size of the full moon for comparison. So again, we're taking really, really big images of the sky here, but with pretty poor angular resolution. Then what we do is we mask out all the stars and all the galaxies and all the things as best we can that we know about, because we're not interested in that. We want to know what's going on in between those. And you get an image that looks like this. And then what you can do is you can kind of reconstruct using statistic what the fluctuations in that image look like. And they look like this. This is you know, us successfully building a map of what the cosmic infrared background at these, you know, near infrared wavelengths looks like. And what we do is measure 5 good fields, and we measured them over 2 flights in this case. And then we do careful combinations and systematic error checks just to make sure that we're not fooling ourselves. And we get images like this. This is at 1.1 micron, 1.6 micron. I don't know how much you all do sort of cross correlations by eye, but I seem to do it for a living. And if you can't see it, I can assure you these 2 images are very, very highly correlated. In fact, they're correlated at the sort of 90% level, if you want to express it in that way. So whatever we're seeing it in 2 independent telescopes with independent detectors. And we're seeing interesting structure on these sort of arcminute scales, or actually 5 arcminute scales. There's a lot of power in these images. So we wrote all that up in a horribly long paper and got it published in Science. It was very interesting. And then the question obviously is, okay, well, you saw, you know, signal, what is it? So the best that we could come up with to explain the data is the following, which is that galaxies, as they grow and merge over cosmic history, they grow by basically eating one another. And this eating one another, you know, being a gravitational interaction, is actually pretty messy. They're not very clean eaters, and they lose stuff out during the process. So this galaxies, as they grow, basically grow these large halos around them. And we know that. And that material is stars, and it's gas and dust. It's all sorts of things. The CIBER result is, in our interpretation, saying that, in fact, all galaxies are sort of embedded in these large halos. And those large halos are what's causing these large fluctuations that we were seeing. So that's the interpretation, is that there's a lot of stuff outside of galaxies. And we know that galaxies have halos. That's not controversial. The question is, how big are the halos? How much material is in them? How bright are they compared to the, you know, what you canonically call sort of the galaxy disk, or if you're talking about ellipticals, bulge. So, long story short, we were very surprised by the result. And we're very surprised because what we saw was very bright. So if you take a sort of notional 10% contrast factor between the fluctuations in the signal and the brightness, which is sort of typical of astrophysical stuff, you'd expect about 15 nanowatts in these funny units. Just for comparison, it's probably easier to see graphically. The light from all galaxies is this green curve, as best we understand it. Now, formally, this is only a lower limit because we can never be sure we've got all galaxies or we've got all the diffuse stuff. But that's kind of, if you stare really deeply with Hubble, for example, this is the kind of answer you get. The answer CIBER gets in terms of the absolute brightness is up here at these wavelengths. So we're missing like a factor of 2-ish, it seems like, by these measurements of the stars in the universe. It could be something more exotic, like decaying dark matter. People look into that sort of stuff, and quote our results. But I would say that's a little bit exotic. But I do think that there are hints that perhaps we're missing some stuff. And as a secondary kind of line about that, of evidence about that, people also make these measurements using gamma ray extinction. They look at very bright gamma ray sources, and the gamma ray sees these infrared photons as sort of a extincting cloud that cause the gamma rays to basically die along the way. And so by comparing the measurement to what they think the intrinsic gamma ray spectrum of these sources is, they can come up with limits on what the sort of sea of photons at these wavelengths is doing. And they get this yellow band. So it's interesting. I don't, I always say to people, I get really uncomfortable getting up in front of a crowd and saying, we have missed half the stars in the universe. I don't want to be, that forceful about it because, this is science and people are often wrong. But we do want to say people maybe should be paying attention. Should we be worrying about our models needing to be corrected or asking the right questions perhaps of the models to make sure that we're getting good agreement here? So we're not done with CIBER. CIBER flew 4 times. The last time was a Viking funeral, and we launched it really, really high on that 4-stage rocket, and it came down in the Atlantic. So obviously it's miles below the sea surface now. We're not getting it back. But what we did do is build a follow-on experiment called CIBER 2. Instead of 2 colors, CIBER 2 is going to have 6 colors. And it's going to go to optical wavelengths. And what that's going to let us do is do kind of experiments where we try to understand what's the spectrum of this stuff doing. And also by going to a single telescope, we're going to get basically 10 times greater A omega, which is this figure of merit that matters in these experiments, and really be able to try and chase after whether this interpretation of intrahalo light is correct or not. So real quick, I'm going to talk, there's a movie down here that'll start playing in a second showing you rocket launch. Real quick, this is CIBER 2. I'm the PI. It's a 28 centimeter primary aperture telescope. And then it gets coupled into 3 cameras back here using very complicated folded optics. 8, 7, 6, 5, 4, 3, 2, 1, 0. So if you're not used to sounding rockets are not like Saturn V's or space shuttles that go like bats out of hell. That was the first stage, and if we hang on for just a second, the first stage burns for 6 seconds. That's the second stage of light. Burns for 6 seconds, and at the end of that, we're going Mach 1.5. This is the second stage burning. It's doing what they call chugging, which means that it's kind of spitting out sparks like a spark plug. That's not good. You can imagine that means that our ride up is not very smooth, but you get what you get. So that's what a sounding rocket is. Basically, it goes up about 300 or so kilometers, and then comes down with a parachute, and we get it back the next morning. So these are recoverable. That's a picture of the that's a picture of the rocket. Our payload, our science experiments up here, and that looks like this if we were to take the skin off. Cool, obligatory rocket movies done. So one of the cool things about CIBER 2 is we're using H2RG detectors, and they're the same types of detectors that are going to be flown on James Webb. So as far as I know, and this is probably not true because the military does stuff all the time, but in terms of civil applications, I think we're the first people to have put an H2RG in space. So that was led by my student who just finished with her PhD, Chi Wen, and she did an excellent job guiding this experiment to its conclusion. We just launched in the beginning of June, so it was 2 weeks or so ago. So very exciting. We're looking at the data now. Okay, so next thought I wanted to talk about real quick is how do you beat the zodiacal light? Well, you're not going to do it from Earth. It's always there, and it's time varying, and it's kind of a nightmare. So the best way to do it is actually get out of the solar system, get away from the sun and the dust in the solar system. So we tried to do this with New Horizons, and specifically with an instrument called LORRI, which was a kind of wideband telescope, basically, that they were using for sort of monochromatic surveys of Pluto's surface. It ends up, as part of their calibration, they were looking at some fields on the way out, 1, 2, 3, 4, sort of taken between Jupiter and Uranus, the orbits of Jupiter and Uranus. And what we were able to do, sort of by trying to carefully understand the instrument, is ask, okay, if I mask out all the stuff that is, individual sources in here, and then make corrections for things like what's the residual starlight in the image, what is the diffuse light reflected back from the galaxy doing, things like that, we were able to make a measurement of the optical background using this thing as basically a light bucket. The data themselves aren't that impressive, but we were able to make a really interesting measurement at a wavelength that's been traditionally very difficult in the optical. So here again, the green band is the counting galaxies, the integrated galactic light. And then yellow again is this gamma ray way of measuring the infrared background. CIBER result is up here. Earlier results from instruments like Derby and IRTS, which were satellites, a couple decades or so ago, are even higher. And our New Horizons measurement, we were able in 2017 to publish an upper limit based on about 6 minutes of data with this instrument. Recently, Lauer et al., working with the New Horizons team, were able to get better measurements using a lot more data that was sort of custom taken for this purpose. And they got these results. So they're also coming in about a factor of 2 higher than the light from galaxies, which is curious. It's sort of difficult to interpret what might be happening here. So I just wanted to advertise that my another PhD student of mine, Teresa Simons, has an even bigger data set that she's looking at right now, and we're hoping to get that published soon. Ideally, it'll come in down around where the IGL is, but we don't know yet. So we're going to find out. And again, if we come up high, it's going to get uncomfortable. We have to start worrying, like, are we really missing half the stars in the universe? Okay. So real quick at the end here, I want to tell you about something upcoming that I'm very excited about. At some point, collaborators of mine at Caltech and other places, we all got together and we said, okay, well, let's consider what are the most important questions in astrophysics. And really, to summarize, they boil down to things like, how did the universe begin? How did galaxies begin? What are the conditions for life outside the solar system, right? These are the overarching questions that we're ultimately trying to answer as astrophysicists. And we scratched our heads and had the experience of CIBER and so on behind us. And we said, okay, how can we build something that sort of addresses all of these questions? What we came up with eventually became known as SPHEREx, which I think you've had a talk, at least in the Astro Colloquium, about this. It's an upcoming all-sky spectral survey. And it's basically designed to try and go after these 3 questions, at least aspects of those 3 questions. So real quick, this is the collaboration. It's what's called the NASA Explorer. So it's the largest mission that NASA will do that's run by a single PI. And that PI is Jamie Bach at Caltech. These are the institutions. Basically, the 3 things we're going to do is map out the large-scale structure of the universe by tracing, doing basically photometric redshifts of all the galaxies out to about a redshift of 1. We're going to try to understand the history of galaxies and emission from galaxies, doing a measurement like what CIBER did by looking at sort of fluctuations in the background light. And then the third thing we're going to do that I'm not going to talk about today, but is of interest, and I'd be happy to talk to you about it, is look for water in sort of young stellar objects and planetary systems and trying to understand where the ice is. So this is what SPHEREx looks like, real quick. It is a 20 centimeter, so, you know, dinner plate size telescope, coupled to 6 of these H2RG infrared arrays. It runs from about 0.75 to 5 microns, and we're doing spectroscopy, low resolution spectroscopy with a resolution of about 40 across that whole range. The nice thing about it is that it's passively cooled. This is how we got it to be relatively cheap by space telescope standards. You basically put these shades around it, and these shades basically reject the heat back out to cold space, and you're able to cool this thing down to about 40 or 50 Kelvin. So that's what it looks like. Very compact. You know, if you had it in front of you, if you exclude the star shades, it's sort of the size of like an office chair. It's not that big by space telescope standards. Because this is a physics colloquium, I wanted to get you excited because you'll hear more about SPHEREx, at least we hope, over the years. It's slated for launch in late 24 at the moment. One of the science cases we're trying to do is inflationary cosmology. So just to give you another view of this thing, from the Big Bang back here, we think that the universe underwent this very rapid explosion in scale factor very early in its history, and that explains a bunch of observations, as I'll get into in a second. It's a very difficult epoch to measure because it kind of gets washed out by other things that happen, you know, much later. And so this is one of the sort of holy grails of cosmology these days is did inflation happen? And if so, can we understand how it happened? You know, what was the shape of this curve? How quickly did it happen? How many E foldings did it expand? Things of that nature. Okay, so inflation was originally postulated to solve problems like why is the cosmic microwave background or why is the universe so uniform wherever we look? If you look in this direction, let's say, and then you look in this direction, you know, 180 degrees apart, the earliest time that those two spots in the universe ever talk to one another is now, right? This photon has been traveling from the cosmic microwave background to us. This photon has been traveling from the cosmic microwave background to us, and the time that they overlap is when they hit us. So why is it that the universe is the same temperature in this direction as this direction? There's either some really amazingly precise cosmic tuning going on to get these temperatures the same within 1 part to 10 to the 5, or we're wrong in supposing that these were never in causal contact, and perhaps early in the universe's history, these parts were in causal contact, and then later were taken out of causal contact and are just now coming back in. So inflation is passing all the tests we can throw at it so far. One of the predictions would be that the universe is geometrically flat. We see that. We see coherent structures larger than the classical horizon, namely that, you know, this side of the universe and this side of the universe appear to be the same, as best we can tell, even though there's no particular reason why that should be. If you look at the fluctuations in the things like the cosmic microwave background, it looks like they're basically scale invariant, but a little bit of a departure, and that's predicted by inflation, and so on and so forth. And that's all basically come from measurements by CMB instruments like the Planck satellite most recently that made these exquisite, you know, high precision measurements. So inflation seems to be like a really hot contender to explain a lot of these weird things we see in the universe, you know, having to do with, you know, its large scale geometry and so on. So what SPHEREx is going to try to do is it's going to try to basically map out the structure of the universe as traced by the blue dots. And in so doing, we know the sort of physics that explains how structures form and how galaxies, at least on large scales, how galaxies form and cluster over cosmic history. So if you think of it as sort of a differential equation or a system of differential equations, once you understand the equations and you have a solution, namely the universe we see around us, Then what you can do is back out the initial conditions. So in a very simplistic way, that's what SPHEREx is going to do. It's going to basically say, okay, I'm going to make a very precise measurement of what this, final state of these equations are. And then I'm going to tell you what the initial conditions must have been. And those initial conditions are these inflationary parameters that we're interested in. So just to give you a sense of what that is, that's parametrized by this funny parameter in the equations called FNL. 1,000 is a very large number and completely ruled out by experiments now. But the point is just to visually show you, because you're not a computer and it's hard to do sort of Fourier transforms in your head. This is an FNL of 0 and this is FNL of 1,000. They're visibly different. The statistics of both the orange underlying stuff and the blue dots are different. They're visibly different. The trick here, though, is you need a large volume survey. You need a lot of measurements of this system in order to really understand it well enough with small enough uncertainties that you can get at what must have been these initial conditions. So just to give you a sense of how we're going to do that, what we're going to do is take measurements that are perhaps not the most sensitive in the entire history of mankind, but sensitive enough, but have very fine spectral resolution relatively, given by the red dots here. And then what we can do is we can take the shape of galaxies and we can fit templates to whatever we measure for an individual pinprick of light in our survey. And by measuring the whole sky this way, we can build up enormous statistics, measure the redshift of 1 billion galaxies very precisely, and really understand what's the three-dimensional position. And once you have the three-dimensional position, you can play this game of backing out through statistics. What must be the initial conditions? What's inflation? What are the inflationary parameters? Just to give you a sense, this is maybe an expert level thing, but just to give you a sense of what the power of SPHEREx will be, this is this FNL number here. This is another inflationary parameter, which is the running of the spectral index. It's how steep is this, index of the initial fluctuations in the universe of place to place. The current best understanding is this blue from Planck, this blue oval here. SPHEREx, through basically different ways of computing the statistics of these three-dimensional maps, can get down to this. And it can really get down to starting to rule out populations of models in interesting ways and reaching the benchmarks that cosmology wants to get to in terms of accuracy on numbers like FNL, so we can really start to make headway in saying what inflation was and what was the energy scale and so on and so forth. Okay, I'm sorry if that felt like a bit of a whirlwind, but I'm done now. So basically, the message I wanted to get across to you is people kind of come with the bias that we need large aperture telescopes to do things. The answer is not always, right? If you are interested in global populations of things or intrinsically diffuse emission, like, for example, the cosmic microwave background, you can get away with small telescopes. And what that lets you do is it lets you get things, for example, into space in cost-effective ways, like on sounding rockets or small orbital things, and really get at interesting questions, more cheaply and easily than building whatever is going to come after JWST. So I think that's about it for today. I will quiet down and be happy to answer any questions you have.
All right, thanks, Mike.